My hometown is near to board. This is my favorite job.
By the way, I wanted to know your mail address. You write somewhere.
Yeah, sure.
In the question, I use the paper though, so it's important to keep which paper. Nevertheless, you write somewhere here. Email. Look, it's so simple.
Yeah.
How do you call Lugo?
Lvo. It's like
With you.
L. Lvo.
Lugo.
Yeah.
It's Alexei, there are too many Alexeis.
That's right.
Okay, thank you very much.
Thank you.
Also, thank you. Yeah. Good. Mm. 2分ぐらいですか。
もう、
マイクはだ、もうこのままI thought of Alexei nine. いつも言うやん。トイレに。
うん。
Don't care, man. Don't care about me. Always like waiting for the flight.
It's still 1 minute.
Very well organized.
Much better than you.
Okay, this right. People are ready. Then let's start the second talk of this morning by Atsushi Takahashi from Osaka University. The title is Set of Full Exceptional Collections and Mirror Symmetry. Please.
First of all, I'd like to organize for the invitation, and I'm very happy that I can give talk here after a long time. It's my first time to give lecture here after what about most of 5 years. And so today I'd like to talk on this subject. So first, I'd like to start from this very elementary thing. So, first, consider the number of factorizations of the cyclic permutation by mu transposition. This number. And for example, I mean by this, by this factorization, I mean this kind of factorization of this particular cyclic permutation. In this case, there are three totally three factorizations, and H, so they or H tilde the from three is three. And in turn, by for example, using Kelly's Labyrinth rooted trees, we want to show this equality. Here, the previous number H tilde is related to, by this formula to the previous so-called previous number, which is the number of coverings from P1 to P1 of degree mu plus 1 modularized model. And so this also on this number H tilde is known by Horowitz in the 19th century. This satisfies this regression form. And obviously, because h to the 0, 1 is 1, we can solve this to get the general. And so also, and later this, but Hurwitz didn't write down proof, complete proof. And later Green found again this recursion. And also he considered the generating function. And nowadays this the curve satisfied by this generating function is known as the run. And also, so this is the simplest case. The case of type a mu. So during consider this in the more general context, or in other words, he generalized this how to say, the counting formula and the recursion formula for finite root systems of AD. Replacing this symmetric group by the white group and cyclic permutation by the coxet. And more precisely, he gave a characterization of set of distinguished spaces and considered the recursion relation. And what he wanted to do is to give a proof for the Royal's conjecture, which is says some coincidence with that number of factorizations and the degrees of reassurance. I'll explain. I'll recall this part later. And about 10 years ago, these people from representation theory gave an interpretation of the previous result with some recursion formula and so on in terms of pre-exceptional correction in module categories of thinking. And what I want to do is to give further generalization by pre-exceptional correction in the derived categories of orthogonal lines with non-negative orthogonal. So in other words, I'd like to generalize them to the affine cases and elliptic cases. Okay, now so in order to state some result, classical result, we call the notion of generalized root system by closed cycle. So this is a natural generalization of the usual classical finite root system. Or in other words, this will be the somehow linear algebra counterpart of the categorical system. So first, I want to consider these triplets, free C modules of rank mu, and symmetric linear form, and some subset of this free module. This delta will be called the set of real and satisfying the usual conditions for every system. We call this subgroup of automorphism of this lattice MLI, the Y group of which is generated by these reflections with respect to this real. And so today, for simplicity, we only consider simply based cases. So I mean, for the finite cases, I only interested in A and D and E types. And so what is important is that the binary form I is not assumed to be positive definite. So we have this radical. And also the point is that this variable is not necessarily a concept. And so because I is not necessarily positive definite, we can consider the signature. And I denote by mu plus, mu 0, and mu minus. And mu 0 is nothing but the rank of the radical. And so I give a summary on this fact for a finite root system. These are equivalent. So I is positive definite, and the set of roots is a finite set, and finite while group is finite. These are the same function. And if these satisfy them, the root system is called finite. And so I omit some detail, but anyway, so in the usual way, we can consider irreducibility, isomorphism, and so on. Then we can consider the classification. And for example, it is well known, but this irreducible finite root system is isomorphic to the 1 of 8. This is a standard result. And from here, it's a bit new. It is due to the cycle motivated by geometry. I'll explain a bit later. But anyway, so first we want to introduce a notion of root basis. It is a subset of words which generate a set of words in this sense. So here WB is a subgroup of while group generated by reflections with respect to these mu words. And from this condition, it follows that N is generated by this B, and also the while group is generated by this, or these are equal. So therefore, in this sense, B will be considered as a basis of the basis. And by in terms of this root basis, we can consider Cox theta M. Because as I mentioned before, the while group is not necessarily a Cox theta group. So there is no natural notion of Cox theta M. So therefore, one needs to there's some characterization or definition of a Cox theta M in this. And this is done by using this root basis. And the element C is called a Cox theta element if there is a root basis such that C is a product of these reflection. And this is in I'm sorry, this also the notch by the cycle. I did these two also. And so the pair, the root system together with this Cox theta element will be called generalized root system. And this is very important. And in general, more precisely, at present, so except for the finite A case, there are several Cox theta elements. So even for the finite D case, there are several in this sense. But and today we use the how to say we will choose several Cox theta elements for the affine A case.
Finite number of them up to
Non-cases, yes. For example, for if we anyway some finite number of Cox. And so for the affine AN case, if the usual extended linking diagram is something like loop. And so according to the orientation, how to say, the clockwise and anti-clockwise direction, we can consider such numbers, how to say, such as the number of how to say, clockwise orientations and anti-clockwise orientation describes a particular concept. And it is classified in such a way. And so this is just a map. Okay, so now you can there is geometry or some construction of root system from geometry, which is the original motivation by your side. And so first I'd like to start from the AD case. So I'll consider these polynomial of AD type. So today, so because here we only interested in geometry, so we can choose arbitrary polynomial defining ADs in. And so the point is that this Japanese algebra is true. The dimension will be denoted by mu. So and this important is that the middle cell, the middle homology group will be a free abelian group of rank mu. Then in this way, what I want to say is that one can recover naturally from starting from F generalized velocity. So first, the free abelian group is nothing but this, and the intersection form, I'm sorry, the symmetric bilinear form I will be the negative of the intersection form because today, or I usually use the polynomial in 3 variables. So therefore, the self-intersection number of the sphere will be minus 2. So in order to have this one, this property, I put the negative sign.
Sorry, may I ask you? So typically, normal fiber should be close to zero. I mean, to the singularity, right? And here it takes R to go to infinity.
Yes, in order to have the smooth one.
And you smooth exactly.
Yes.
So you meant to say it does not matter.
Yeah, that doesn't matter, yes. Yeah, but later I want to deform small f to large f. Well, yeah, we want to consider later as a universal holding. So I from the beginning I choose the some real number large enough. So you should, so in order to, if you are only interested in the root system, this can be just one. And so, because we know the result, so we define the set of roots in this way. This is the special property for all the finite case. And so what is important is the last one. So one can consider the minor monotopy. It is the image of the monotopy representation is the generator. And this tuple will be a finite system. Sorry. The first triple will be a finite system. This is well known. And also, together with this, this defines a Cox diagram. And in this case, this will be the standard one in the, how to say, probably what many people know. And anyway, this will be, in this case, if we choose CF in this way, then the CF is the standard Cox diagram. And this tuple array with this constant element will be a general. This is the typical example. And so therefore, so in terms, so in this way, it's a general result, but by cycle, but in this way, if one define tuple in this way, then one gets generalized result. This is the geometric construction of the generalized root system.
And this, yeah. And there is also some non-linear, non-symmetric bilinear form, like in the previous talk.
Yes, so it is not, in some sense, this is a symmetrization of the form. So the, how to say, upper triangular part or something like that is known as the Seifert form. Yes.
So you don't consider it?
This
was Professor Saito did.
Yep, it's a little bit, how to say, so this symmetrized one can be defined purely in terms of the algebra, or how to say, its type form is a little bit more geometric object, so I prefer this. So, but in this order. Also, in this case, from if in some special cases, starting from this symmetrized one can recover the how to say Euler form or the Zeta. I'm sorry, I don't know the more. It's and now I want to further explain a bit on the distinguished basis. So I deform small f in this way, and this is called the universal quality. And so this by this m I denote the parameter space, and this is chosen so that the conditions are satisfied. Yeah, today I skip this detail, but anyway, there is a standard way to choose this monomial. And for example, we so in the case of type A, we can just the monomials, and this is the example of type type D4. We can consider this deformation. So by using this logic, we'll consider some geometry of critical points and critical values as well. And so the important is this. So in general, so with multiplicity, there are mu f critical values, but consider this subset where the restriction of f has less than mu f critical values. Sorry, critical values. So therefore, by definition, if we consider this parameter is outside this bifurcation set, then this large f will have mu f exactly mu f critical. So therefore, we have a correspondence between or S and set of critical values. And this will be a map from this M minus B to this configuration space of mu f points on C. And this is the important map, and it has a name called dash following map. Which we denoted by LA, just simply LA. And it is known that this map, but by considering it carefully, but it turns out that this map will be forming. But moreover, what is important is that this map is an unramified covering. And it is very important. And also, we can rather easily calculate the degree of this map, which is given by this degrees and the mu value. And but here, degree is normalized so that the degree of small f and large f will be one. And so I will explain in this example. So starting from this polynomial of type A mu, we can consider by adding these monomials to the universal quality. In this case, mu f is nothing but this mu. And by this rule, we can calculate easily the degree of SI. It's given by this. Then by calculating this number, we can easily see that this is mu plus 1 to mu minus 1. This is equal to the h tilde 0, mu plus 1 in the so this appeared in the introduction part. So anyway, so by this observation, so we have a very interesting quality. So this is the degree of this holomorphic covering. On the other hand, this is the number of factors, and this equality means they coincide. Okay, so before giving precise statement, I want to continue to explain distinguished spaces. So we consider the how to say set of critical values in C, and we can put an order on this set by introducing this ordering. Anyway, so this is in some sense the usual way to define an order of in the how to say study of the homological mirror symmetry, and it's I should mention that this ordering is the opposite to the classical one in the singularities. And I wrote some technical detail, but anyway, so starting from the critical value, we can consider path starting from the critical value to this is goal, the fixed point, the real number large enough. Then to each path, we can associate vanishing site. The point is that it is defined up to site. But anyway, some homology class represented by a two sphere, which is called vanishing cycle along the path Pi. Then we can consider according to the previous ordering, we can consider the ordered set of the vanishing cycles, and which is called the distinguished basis for vanishing cycles. And so, as I said before, so this is defined up to sign the choice of these paths. And because how to say some the critical values, the set of critical values defines a point on this configuration space, then naturally the fundamental group of this one acts on the set of distinguished spaces. So it is nothing but the Alkin's Braid group. And also this sign change acts on this set of distinguished spaces. So therefore totally this group generated by a Braid group and the sign changes group this naturally acts on the set of distinct basis of function sets. So this is the anyway. So this is it is how to say some homology version of the Braid group action the action in the previous talk. Anyway, so yeah, I think many people are very familiar with these actions. But anyway, so this is this group action on the set of this equation. And in particular, in the geometric side, and on the set of distinguished bases, this group acts transitive.
For each f.
For any singular, for any polynomial defining a singular.
Isolated. For any polynomial defining an isolated singular.
Isolated singular, yes. So yeah, maybe now I should say so. There is a subtle difference between distinguished basis and free exception. Distinguished basis will define an exceptional correction, but any free exceptional correction may not come from a distinguished basis, even if we hit a homological.
This is some numerical action, right?
Yeah.
What's you need a global of operations.
For general, probably two. Yeah, at least broken evidence says so. I don't know the proof.
Kind of operation is only local subset.
Yes, yes.
For general, you need the global subset.
Yes. Yeah, I mean, so interesting subtle part, but on the settle, so anyway, so there indeed there is full exceptional correction which doesn't come from the decision basis, even if we consider the Fukai. Okay, so this basis defining a full exceptional correction, but the full exceptional correction may not come from this basis. There is a difference. So anyway, this defines what to say. All this group action. So maybe I just want to type this is so we consider so in order to choose distinct spaces, I need to choose a point outside the bifurcation state, and also yeah, yes. And so the first problem here is that we need also to choose an orientation to sphere. But if we consider the quotient set, this was the sign change group. The ambiguity is now cancelled. So, and on this set, still the brain. So therefore, it's distinctly important from it to understand the relationship between this point and the distinct space. And the previous solution, I mean, this one, this transitivity of the brain of reflection gives anyway is a surjective map from this space to this set. And Ryan conjecture that the cardinality of this set should be equal to the degree of the Ryan map. It is equivalent to the equation that there is a bijunction between a set of suitably defined conductive open subset in this space and this set. So I mean, so because from here to the configuration space, there is a covering path. So if we choose, so I mean, this conductive open subset means this one good conductive subset in the configuration set, and also the some inverse image. And so in order to relate the distinct spaces and the offset element, we just this is a remark for the relationship. So in order to consider the distinct spaces, we need to consider the larger, not the smaller. But by considering the how to say some parallel transport in some sense, we can consider the some group homomorphism from this phi1 to this fixed automorphism group over some fixed phi1. And this consideration is this equality. Coxeter element can be the product of these reflections with respect to the distinguished space. And so, in other words, this distinguished basis defines a root basis. Yes, so in the previous slide, I just said that distinguished basis defines a root basis, but in the finite case, opposite hold. This is known as the Dirichlet result. This capitalization of the distinct spaces. So this is this means the right hand side is a subset of the left. So I mean, so if we consider the ordered type of roots satisfying this condition, then it defines a distinct space. This is the homological capitalization of the distinct space. And in particular, in in the in other words, we have this quality, this isomorphism, one-to-one correspondence between these two sets. So therefore, if we consider the root system or the polynomial of type A, then this is nothing but the set factorization of the cyclic permutation. And now by this, it is this can be considered as a set of the distinguished basis modulo psi. Okay, so now so it's in general very or quite difficult to find a distinguished basis in the geometric side. But if we have this equality, then it's now a problem in linear algebra. Okay, now I'd like to state the derivatives result. And this let Q bar be a Coxeter linking diagram for finite root system. And but here I mean this as a root basis, we choose the simple root basis or simple base in the usual sense. And so therefore, so Q bar is just the usual link diagram, so for the link. And also, so for simplicity, I allow the non-connected one. So maybe Q bar can be the product of the irreducible linking diagram. And then define this by this E of Q bar, the cardinality of this set of factorizations of the Cox type. Then we show this recursion formula. And here, Q bar with this small b is the subdiagram of Q bar given by removing the vertex and arrows connecting with B. And this H is the order of the Coxeter element, the usual or standard Coxeter element, which is known as the Coxeter number. By solving this recursion, one has not easy, but anyway, one gets as I exercise this point. So here I rewrite in the other page. So here D1 to D mu are degrees of algebraically independent white grouping variance. And this by the previous proposition, this cardinality is this degree of the diaspora. And of course, the point is that this was the parameter space of the universal holding, and it is the nothing with the space of the white grouping. Okay? So, and I'd like to explain in this example the case. So in this case, large F, the universal unfolding is of this form. So by the degree, the rule, degree of S1 is 1 and so on. And it's easy to calculate the degree of the Ashkorek and this is given by 160. And on the other hand, one can solve the Dirichlet's recursion formula in this way. So starting from the usual thinking diagram of type D4, we can choose four vertices. And if we remove, how to say, edge vertex, then there are three edge vertex. We have if we remove such a vertex, we get A3. And if we remove the central vertex, we get A1 cross A1 cross A1. Then so by so because we can, how to say, exchange the order of because this is just a direct product, so the reflection commute. So we have this symmetric factor, and by assumption of the induction or regression, we get this these are. This is the example.
So 1 minus 1, isn't it 0?
And so it's 1 minus 1.
Yes, and the
Yes,
last-
0. Yes, therefore 1. So all 1. And so E of A1 is just 1. So the cyclic permutation 1, 2 is nothing but the one. So E of A1 is nothing but 1. But here I just simply put in the, let's say, recursion form. Again, we consider the categorification or in the so far we consider I consider the level of linear algebra, and so I would like to upgrade everything in the category. So in order to do that, we need the notion of exceptional object, exceptional collection, and free exceptional collection. But probably many people know this, so I skip this part. So for simplicity, denoted by this FEC of T, the set of isomorphic classes for exceptional function in T. And also, this is well known and also appeared in the previous talk. There is group action. This action on the set of pre-exceptional function. This is due to the question. And also, I'm interested in the action of auto-equilibrium balance D. Well, no, sorry. No, this is not D, but T. T. And also. And so, I mean, the auto-equivalence group acts from the left. I think this is well known. And so here, it's not difficult, but to connect the, how to say, categorical and the language root system, I make on this. So, so first I assume these two conditions. So the transitivity of this group action on the set of exceptional collection, and also here I need any exceptional object can be completed to the free exceptional collection. So this condition can be weakened, but today for simplicity, we assume this because the triangulated category appear today all satisfy these two conditions. These are very strong, but it is enough for today's purpose. Anyway, on this setting, so I mean, first, so anyway, T admits of the exceptional collection and satisfying these two conditions, then we can recover generalized resistance in a very natural way. So the free abelian group is the Grothendieck group. And the symmetric binary form is nothing but the symmetrized Euler form. And this is a little bit technical, but in this way we define a set of groups. And Coxeter transformation is very naturally defined in terms of self. Sometimes S with this -1 translation is called the Coxeter transformation or also underwriting transformation, translation. But anyway, the induced automorphism defines Coxeter elements for these roots. Okay.
Excuse me,
Yes.
I am missing. What was B in previous page?
B is a crossover. Sorry, I
You
have
choose-
right.
What is?
B. The cross of these phrases.
You choose one.
Yes. Yes. we choose one, but later it turns out that this doesn't depend on the choice of E. This is why we record the results for linking limits. And in this case, these two assumptions are known by this Tronikov and Ringer. And consider this number. Because to say so, obviously the set of free exception collection is an infinite set. So we first divide by the translation action and consider this number E of Q. Then these people from representation theory show the exactly the same recursion as the recursion. And also,
Sorry,
yeah,
what's the definition?
even this. This is a set of the free exception.
You mean the cardinality?
Cardinality, yes. So that. Well,
The number.
consider this set and divide by the topic.
The number of orbits of
and it can be obtained. And obviously,
sorry,
yeah.
that means what?
The reason just no.
The shift
The
here.
translation business.
I think the number of exceptional collections up to shifts of
Yes.
the objects, right?
Yeah. So therefore, in this case, it's nothing but the set of free exceptional collection in the module category. And obviously, in this case, how to say, initial data can be easily calculated. And so, because E cube was the set of factorization, this one, and this satisfies this recursion, and also this one, and without the same recursion, and the initial data is the same, so therefore we get these are the same. So in this way, so they categorify the linear regression or such a number of categorization in terms of the free expression.
So what is Q0?
Q0 is the vertex set of Q. Usually, so Q is usually denoted by the pair of QL. Couple of Q0, Q1, and S and T, so on, something. Q0 is vertex, a set of vertices.
Is there any reason behind this formula?
I'll explain the next. Yes. So essentially, these are the some idea of the proof. So in order to consider or to classify the free exception collection, we need to consider the how to say the last. We need to consider the classification of the last object and the set of free exception collection in the also one. This is the key idea. But on this part, the first part, classification is the last exception object. Due to our optional identity, choice of this exceptional object, modular Coxeter factor or optional derivative translation is nothing but a choice of the buttons in the linking quiver. And obviously, as I said, so by choosing suitably the integer, this object can be considered as module. And also, this is the important property to give this front factor. The zeta factor or the outside right hand translation is of order h up to this twice of the translation. Therefore, we get this in order to classify the last object. We need the vertices in the linking quiver and also this factor by this. And this part we can consider regard our integration process. And so the point is that the orthogonal is again there's some or not it's nothing but this is maybe I'm sorry this is equivalent to this direct category. So therefore we not very naturally we get this regard. Essentially this. Okay, so now I comment a little bit on this subtle difference or relationship between distinct spaces and flex. And flex, so I omitted some part, but anyway, so distinct spaces can be categorized into direct, so-called derived category or directed category, the left hand side. And due to side, this equivalence is known. And in particular, the distinguished spaces can be categorized to free expressional collection in the left-hand side. So therefore, we have a natural inclusion of sets starting from this. Distinguished spaces, modular sign, and this can be embedded into free expressional collection of the entire side, modular translation. And by this equivalence, we get. But it's important that these maps are all brain group equivalent. And also this on the both hand sides, it's known that the brain group action is stored. So in this case, the cardinality of this set is not the EQ. It's as expected. So therefore, in particular, in this case, in the finite case, this transitivity of brain group action implies the any full expressional collection comes from the distinct space. Okay, this is the main of the main part. But so what I want to do is to generalize the previous one, the finite case, to the affine case and the elliptic case. But the problem is this how to resolve the non-finite. So I explained by using this example. So first, consider general root system that between A1 type.
So non-finiteness of what?
Non-finiteness of many things. So for example, while group and the set of roots, and also the set of full exceptional collections and many things. So finite case, so if something is finite, then usually it implies the original root set is finite. And in this case, we can consider this typical example. This choice of root basis. This is not simple basis, but it is very convenient. So in this case, because now it's the root series of a finite type, we have a radical, and in this case, radical is rank 1. Then so we get in this case, we have this. For any integer k, the Coxeter element can be factored into these reflections. So there are very naively infinitely many factorization of Coxeter factor in terms of reflection. And obviously, so if we consider this, reflection collection modular translations is can be identified with this set. Obviously, this is infinite. And it is related by this condition. But on the other hand, the interesting point is this observation. The set of set of quantum matrices is fine. So therefore, from this observation or this calculation, it's very natural to consider taking a further quotient by this autoequivalence. Then in this case, we'll get 1. So in order to state some general result, I briefly recall this construction of the overall. Just these consider A a double of positive integers, which be the orders the isotropy at R of time, and consider this quotient ring. And on this, we have a natural gradient, different values. Anyway, almost. And by using this ring R and grading L, the orbital line is defined in this way. And by using this, large A, we can consider this number chi A, orbital Euler characteristic. And I want to consider these two cases, a positive case and Z case. And this first part corresponds to the affine case, and the second part corresponds to L. This is well number. And also, I just skip this part. But anyway, so this category admits a fully exceptional position due to guide lensing. And the method, this group action is transitive on the set of exceptional collection. And also there is several categorical equivalencies. For example, we can use this diagram on this equivalence relations. And in this case, mu will be this number. Anyway, so it's difficult to list all names, but so therefore this I just said about summary from works by many people. But anyway, these we have homological mirror symmetry equivalence and so on. And here we have extended linking quiver associated to the numerical equation A. And so this small fa is this one, which we call a polynomial. And so according to the classification A, it corresponds they correspond to these types. And so here, because affine A case, as I said, the extended linking diagram is a loop. So we need to choose an orientation, and the orientation define how to say classifies several Coxeter elements, and according to that, we and in this case, one PQ case, this can be reduced to the one variable model. And in this case, so the story will be the some rational function on PQ. Anyway, so I try to continue. And so consider universal unfolding of this previous small FA. It's written in this way. And the parameter space will be this. And S mu is the parameter, the coordinate of this one.
This rational function on the previous slide.
Yeah.
Is it a kind of mirror?
Trying
to mirror.
Homological mirror symmetry equivalence. The last. This together with the choice of primitive form gives a mirror. Or this together with the choice of primitive form defines a classical mirror to this one.
If this also said it's possible to choose just one.
Yes, yes, yeah, of course, we can choose different models to give the same for progress structure. Like sometimes to use this model is very simple, and to use this polynomial, it's more systematic. It's very different, which we should choose. But anyway, so still, in we can put degrees on these variables. And the point is that chi is, we assume that chi is positive. So therefore, all parameters are of positive degrees. So we can calculate the Diash-Correlation map, degrees of the degree of the Diash-Correlation map just by using these degrees. It's let's say, so by using generalized basis theorem. Anyway, so the final result is this. This is again the bifurcation set of this. Now we have this has a fundamental group. So and MA can be considered, but based on the philosophy of homological graph symmetry, MA should be the quotient of space of stability condition divided by the fundamental group. So in order to get the finite number starting from the full exceptional collection, then it's natural to consider the quotient by some suitable subgroup isomorphic to C. So this is the idea, and also the space of stability condition can be considered as a generalization of type Miller space, and this auto-equivalence group can be considered as a generalization of the mapping. So altogether, based on all these philosophy, we consider this. We come to this group. So here I consider this one is the D denotes the sum product of the Dirac category of the orbifold and linking ribbon. And consider the subgroup of autoequivalences generated by spherical one spherical space. Then we consider this number. Now, not only this, but we divide by this automorphism. And if we consider the thinking quiver case, then there is no spherical object, so this is the trivial group. So this definition reduced to the original previous one. And also important fact is that so if the also one complement of the some solutional object is again always of this form. This we use this special property. Now we can say the main one main result. And in this case, we can count. First, we have this isomorphism, or we can determine this ST group ST, and also it's possible to calculate this numbers, and we see the coincidence with the number of exceptional coefficient modulo this isomorphic autoequivalence with the degree of Diash-Correlation. Sorry, and I have no time, so please skip main part. But anyway, so the stability is the almost the same, and we use the recursion. And now we have an extra term here. This is due to the answer-underwriting quiver consists of the so-called main part containing the exceptional vector bundles, and also the some connecting component consists of chips. And these two terms correspond to the main part and chips. So if we so this corresponds to the V correspond to the exception character bound, and here corresponding to the exception shifts supported on the overall function. Then we get by considering a similar story, we get this diversion, and we can solve this, and we get the previous one. And I'm sorry, I skipped this part. Also, we can compare with the previous numbers if the A is 1 cube or type A. Anyway, I just showed the result on the elliptic case. So in this case, elliptic simply the universal unfolding of the simple singularity. We choose for example, the Legendre normal form, and so we consider this parameter space. Then again, similarly, we get degree diaspora map, and the degree of diaspora map is calculated by everything Brucker and so. And also in this case, it's a little bit different because the group generated by spherical space is very large. In this case, the essentially the principal congress sum. I skip the explanation way. I'm sorry, here anyway. Something like this. And also we get the this figure. So in this case, labs are guided quiver consists only how to say tubular connected components. So we only have the second part type patterns. And anyway, we get. And finally, again, in this case, by calculating some something, we get the coincidence with the degree of the scoring hammer and the number of free expressional corrections modulo some principal congruences. So I'm sorry, I don't know. So I asked to thank you very much.
Thank you very much. So, any question or comments or say? Yes, please.
It's a more complicated case. Can you treat more complicated case except ADE?
AD, it's possible to consider, but yeah, I'm trying to understand, but I don't have a conjecture, but I don't have a proof yet. So, so we can consider some categories corresponding to the previous numbers. It's assumption really easy.
Any more questions? Yes.
For example, if you consider weighted projective line,
Yeah.
why?
Yeah, in case I don't expect we get the finite number because in that case, set of exception function will be larger, but the set auto equivalence group will be smaller. So therefore, we cannot. It's, or I think impossible to get a finite with that.
I have another question, but better discuss later. Okay, so let's thank the speaker again. End of morning session. Is there any?
Just we make it at 12 o'clock. Resume. Resume at 12. At 12 o'clock. At 2 o'clock.
2 o'clock.